New York State, Algebra 2, Regents, Common Core, Basic Graphs of Inverse Trigonometric Functions. The range of the inverse sine of x, sometimes referred to as arcsin of x. Concept number 14. Now, the odds of someone doing exactly what I tell them to do is pretty slim, but I guarantee that if you cram with me, you'll become an Algebra 2 master. So inbox me at memedicine@gmail.com to order this complete cram session. If this isn't the subject you're looking for, no worries, still inbox me at memedicine@gmail.com to order personalized packages for alternate subject areas. Be sure to spread the word to your friends and classmates who also need to cram. Now let's cram the topic of the range of the inverse sine of x. Basic graphs of inverse trigonometric functions. The range of the inverse sine of x, sometimes referred to as arcsin. Let me show you what I mean by this. Arc sine. Okay. All right, so the key to cramming through this is putting things in order. Before we get into the actual concept, I need to do some pre-concept review with you, okay? So here we have our xy, Cartesian coordinate plane, and an acute angle in standard position. When I say an acute angle in standard position, I mean that the vertex is at the origin, the initial side ray going to the extent of its x coordinate is on the positive x-axis, and the terminal side ray ends in quadrant 1 to the extent of its y-coordinate. Okay, and it's acute again because it's bound between the quadrantal angles 0 degrees and 90 degrees. And the reason why we're referring to the angle as theta here rather than x is because in this pre-example, x represents the x-coordinate, the extent of the initial side or the adjacent side to the angle. So we don't want to double up on variables. If you resolve the terminal side rate again into the x-coordinate and y-coordinate, what you get is the formation of a right triangle, okay? And because this angle is in standard position due to all the features I just previously mentioned, it's referred to as a reference angle. So we know that when we calculate the inverse functions of any value, whether it's inverse sine, inverse cosine, inverse tangent, arcsine, arc cosine, arc tangent, the answer that you're going to get is an angle. But what you're getting is a reference angle, an acute positive angle in quadrant 1. That's what your calculator knows how to calculate. It doesn't know how to differentiate between a reference angle, an angle in quadrant 2, an angle in quadrant 3, or an angle in quadrant 4. Some do probably, but you would have to specify specific parameters in order to do that. So what you would then have to do is do a little bit of manipulation in order to calculate the trigonometric values for what seems like a reference angle, but it actually isn't. Let me show you what I mean by that. Let's say the value of this reference angle was 40 degrees. And let's say you did a vertical translation rather, and you flipped it over here into quadrant 2. But you're not interested in theta or theta reference. Let me write out that subref so you can know exactly what I'm talking about. It's supposed to be an REF. So when you see that, it's just referring to the acute reference angle. Where you're actually interested is in this angle. So in order to calculate the angle that you're actually interested in, you would have to subtract the reference angle from the extent of quadrant 2, which is 180 degrees. So 180 degrees minus theta ref, or 40 degrees, is going to give you the actual angle value you're interested in of 140 degrees, okay? And let's say you're actually interested in an angle in quadrant 3. So you would have to basically flip the reference angle. Sorry for the non-scale drawings over here, okay? And in order to calculate this angle that you're actually interested in, you would have to add 180 degrees to the extent you would have to add this reference angle to the extent of quadrant 2 all the way in quadrant 3. And so that would be 180 degrees plus 40 degrees. That's going to give you 220 degrees, okay? Likewise, let's say you were to flip the reference angle about the x-axis to wind up in quadrant 4. Now, in order to calculate this particular angle of interest, what you would have to do is subtract the reference angle from the extent of quadrant 4, which is 360 degrees, as well as 0 degrees. But you know, once you do one full revolution, this 0 degrees becomes 360. So 360 minus theta ref, or theta, is going to be 320 degrees, because remember, for this example, our reference angle is equivalent to 40 degrees, which is an acute positive angle, okay? All right, so that's that. Oh, another thing that you need to get straight and organized in your mind is that the x-coordinates can be positive in quadrants 1 and 4, but negative in quadrants 2 and 3. Likewise, the y-coordinate can be positive in quadrants 1 and 2, but negative in quadrants 3 and 4. So this is going to affect the value of trigonometric functions, okay? And for inverse trigonometric functions, I think it's always going to calculate the positive value. Yeah, that's why it's calculating the reference figures. Okay, so that's like a long aside, but this is still not the pre-example that I wanted to tell you. This is what I want to demonstrate to you. In order to establish the sign of some angle theta or x, you actually have to know what the sign is. And the sign is equivalent to the y-coordinate, not the measurement of this side y, divided by the measurement of the terminal side ray r. So r, or the hypotenuse, the denominator is always going to be positive, because what you're actually incorporating is the measurement of the length of the hypotenuse, or the longest side of the triangle, okay? Yeah, so that's that. And so y coordinate over r equals the sine of theta, or, you know, let's say we weren't calling this theta, it could be x, whatever variable system you're using. But when we take the inverse sine of this entire equation, what we get is the inverse sine of y over r equals the sine of theta over x. Okay, duh. Now what? So as we continue and we distribute the inverse sine function, the inverse sine of y over r is equivalent to the inverse sine of the sine of theta or x. Okay, this is highly repetitive, but what you have to know is that when you start to evaluate this, you get that the inverse sine of y over r is going to be equivalent to the angle theta or the angle x, whatever variable system you're using. Because when you take the inverse sine of the original sine function, it will cancel out that sine function on the right-hand side, okay? So yeah, inverse sine or inverse trigonometric functions undo the original function, like the base functions such as sine, cosine, secant, cosecant, all those things, okay? All right, I think we've done some pretty good establishing of concepts. Now on to our original Cram session. Is there anything I'm forgetting? Oh yeah, the triangle doesn't have to be a right triangle in order for you to calculate the sine or cosine or tangent of the angle, okay? It doesn't have to be in a Cartesian coordinate system either. What is the range? And when I say range, I mean all the possible independent dependent variables rather of a function, of the function y is equivalent to the inverse sine of x, sometimes referred to as the arcsin of x. Definitely press pause and think about your answer, and also draw a graph to demonstrate what you're thinking in your head. If you don't know how to do this yet, because it's more easily said than done, that's fine. Just sit tight, take a breather. We're going to get into it anyway. All right, so hopefully by now you were able to press pause and come up with an answer. And if not, that's completely fine. This is going to take a brief moment, not too long. All right, so here we have another Cartesian coordinate plane. And I want you to recall again that the inverse sine of x, this you should have learned, and if you don't know it, now you're going to know, is the inverse function of y equals the sine of x. Okay, so here goes our y equals sine of x function. And the y equals sine of x is not a one-to-one function. It is a legitimate function. All legitimate functions have to pass the vertical line test, which it does. The vertical line only goes through it once. But what it does not pass is the one-to-one function test, which is the horizontal line test. Okay, see at several different places it intersects the y equals sine of x curve or function several times. Now this will ultimately have an effect on the range of y equals the inverse sine of x, because our inverse functions originate from our original trigonometric functions. Okay, so in order to determine the range, the domain of the y equals sine of x function has to be restricted. And if you watch my Cram session on the domain of the inverse sine of x, you would know exactly what I'm talking about. Remember, the domain of a function is a set of all possible independent variables, usually x values. Okay? All right. So yeah, we're going to restrict the domain in order for ultimately y equals the inverse sine of x to become a legit function. Now this can be restricted arbitrarily from here to here, there to wherever, but typically in the world of trigonometry, we restrict the domain between negative pi over 2 to pi over 2. And this is the region that's going to be used to generate the one-to-one region for the inverse sine of x. So ultimately, you're going to find that the range of the inverse sine of x is going, well, the range of the sine x function is going to be restricted between -1 and 1, okay, because we're restricting the domain from negative pi over 2 to pi over 2. So whenever you restrict the domain, a restriction of the range ultimately follows. I think that makes sense to you. Now, what we have to do is to create the graph of y equals the inverse sine of x. And in order to do this, we have to reflect the graph of y equals sine of x about the line y equals x. This is the line y equals x that passes through the origin. And let me just tell you, in order to find the inverse function of any function, it doesn't even have to be just trigonometric. All you basically do is reflect the original function about the line y equals x, but sometimes it's not easy to visualize this in your mind, okay? And that's what we have to do to get our y equals the inverse sine of x graph. And notice that when we do this, you get something that looks like this, and reflection about the line y equals x automatically just switches all the x and y values. So when I say that, notice here pi over 2, which is the original extent of the domain of y equals sine of x, becomes the extent, the initial point for the range of y equals the inverse sine of x, and vice versa. Yeah, so basically you're just switching the domain and ranges, or the x and y elements, x and y values, okay? So again, you're going to notice that now this black line represents the inverse sine of x, and its domain is -1 to 1. And the range, the answer that we're looking for, is going to be -π/2 to π/2. Okay, so let's neaten things up a little bit. Here goes our restricted y equals sine of x. Y equals the inverse sine of x function. So notice that the π/2 or radian measures are switched to the y-axis. Okay, therefore the range, again, is going to be -π/2 is less than or equivalent to y, which is less than or equivalent to π/2. So inverse functions, you're basically exchanging the elements of the domain and ranges to get from the original functions, all right? Hopefully I didn't tongue twist and confuse you too much. If you are, just break this video up into 5-minute intervals, take breaks, come back and forth, but trust me, you're going to learn. Maybe it's just going to take repeating this a few times, and definitely don't play it slowly. Play it on 1.25 speed, 1.5 speed if you need to. We don't want to spend our whole lives on this. All right, our goal is just to get an A, not to grow old learning trigonometry.